All right, let's dive right into a really big question, one that sits at the very heart of physics. We know that everything, you, me, this entire planet, it's all built from these tiny quantum particles. And the rules they play by? They're bizarre, almost like magic. So here's the puzzle. Why isn't our world just as weird? Why doesn't reality feel as strange as it should? That's what we're going to unpack today.
And this isn't just some hypothetical, what-if question. It really gets to the core of the problem. You've probably heard of Schrödinger's cat, right? The idea that a cat in a box, its fate tied to a quantum event, is somehow both asleep and awake, or more famously, alive and dead at the same time, until you look. But here's the thing. We never see that. Ever. We look in the box and the cat is one or the other. So what's the deal? What's acting as the bouncer, keeping all that quantum weirdness from getting into our everyday reality?
Okay, so to figure this out, we need to look at the secret ingredient, the one thing that really sets the quantum world apart from ours. You can think of it as its secret superpower, and it completely flips the script on how things are even allowed to exist.
And honestly, the whole difference comes down to one little word. It's the difference between or and and. Think about it like this. In our normal classical world, a computer bit is basically a light switch. It's either off, which we call a 0, or it's on, a 1. That's it. It's one or the other. But a quantum bit, a qubit, is more like a dimmer switch. It can be a little bit of off and a little bit of on all at the same time. It can be 0 and 1 simultaneously. And this state, this bothness, is what we call superposition. It's the engine that makes the whole quantum world go. So you have to wonder, what holds this incredibly delicate and state together? Well, there's a special property for that, and it's called quantum coherence. I love the analogy of an orchestra conductor. Coherence is what keeps all the different possible states, the 0 and the 1, playing together in perfect, stable harmony. It makes sure they have a predictable relationship. You take away the conductor, you take away coherence, and the whole thing just devolves into noise. No coherence, no superposition. Simple as that. The quantum magic just vanishes.
Let's make this even clearer. Just think about the difference between a light bulb and a laser. The light from a regular old light bulb, that's incoherent. The little packets of light, the photons, are just flying out every which way. They have random phases. It's like a huge disorganized crowd where everyone is shouting whatever they want. But a laser, that's a whole different story. A laser is coherent. All its photons are marching perfectly in step, totally in sync, with their phases all locked together. It's like a highly disciplined marching band. That's the kind of beautiful order that coherence brings to a quantum system.
But here's the catch, and it's a big one. This amazing quantum superpower, this perfect coherence, it's incredibly fragile, like ridiculously fragile. The tiniest little nudge from the outside world, even something as small as a single glance from the universe, can shatter the whole thing. So, how does that happen?
Well, to understand that, we have to call our star witness to the stand. And it happens to be one of the most mind-bending, most famous experiments in the history of physics, the double-slit experiment. This one experiment shows us not just that quantum weirdness exists, but it also reveals exactly how it vanishes into thin air.
Okay, let's break this down. First, imagine we're shooting tiny particles, like electrons, one at a time towards a wall with two little slits in it. We don't watch to see where they go. What happens? On the back wall, we don't get two simple lines. Instead, we get this beautiful wave-like interference pattern. The only way that pattern can form is if each single electron went through both slits at once. It's a perfect demonstration of superposition in action. But now we get curious. We put a little detector right by the slits to see which one each electron actually goes through. And the second we do that, poof, the wave pattern is gone. It just vanishes, and instead, we just get two boring lines exactly where you'd expect them if the electrons were just tiny little bullets. Just by looking, just by gathering that little piece of information, we completely change the outcome.
So, what in the world just happened? This is the big question, right? What did we actually do? We didn't touch the electron. We didn't block it. We just looked. We observed it. So where did all that amazing quantum weirdness, that beautiful superposition, just disappear to? The culprit has a name, quantum decoherence. And here's the key idea. Anytime a quantum system interacts with its environment, and I mean any interaction, even a single stray photon bouncing off it, a little bit of information about that system's state leaks out into the wider universe. The universe itself basically becomes a spy. It finds out which path the electron took, and as soon as that secret is out, the superposition is shattered. The magic is over.
And this isn't some abstract philosophical thing, it's a real physical process. That little photon we use to see the electron, it's now entangled with it. It carries a tag, a piece of information that says, hey, the electron I bounced off of went through the left slit. And because that information now exists out there in the environment, the two possible paths for the electron can no longer interfere with each other. The secret's out, the superposition collapses.
Okay, so this is where it all comes together. This whole process, decoherence, it isn't just some weird thing that happens in a lab. It's happening everywhere, all the time. It's actually the fundamental reason our world feels so, well, normal. It's the bridge that connects the weird quantum world to the solid, classical reality we all know.
And this is why your cat is never both asleep and awake. Think about it. A big object like a cat or a bowling ball isn't isolated. It's constantly getting hammered by its environment. We're talking billions upon billions of air molecules, photons from the lights in the room, heat radiating off the walls. Every single one of those little interactions is a tiny measurement. It's like the universe is spying on the cat with a billion tiny cameras all at once. This constant, overwhelming flood of spying forces the cat into one single definite state, so incredibly fast that the superposition is gone. Before it even has a chance to exist, it's decohered almost instantaneously.
And this quote just nails it perfectly. Classicality is an emergent feature selected by the constant monitoring of a system by its environment. Wow. Think about what that means. The solid, predictable reality that we live in isn't the fundamental layer of things. It's what emerges. It's what's left behind after the universe has spied on all the quantum possibilities and forced them to pick a side.
Okay, so this isn't just philosophy. This has huge real-world consequences, especially when we talk about technology. Because if you're trying to build a quantum computer, decoherence isn't just a curiosity, it's your absolute worst enemy. It's public enemy number one.
See, the whole point of a quantum computer, the source of all its incredible power, is its ability to use coherence and superposition. But decoherence is always there, this constant background hiss, trying to tear it all down. So building and running a quantum computer is literally a race against the clock. You have to get your calculation done before the environment spies on your qubits and they just turn into boring old classical bits, losing all their power.
And scientists actually measure this race using two different stopwatches, T1 and T2. T1, or relaxation time, is basically how long it takes for a qubit to just run out of energy and fall back down to its ground state. But often, the real killer is T2, the dephasing time. This measures how fast the delicate relationships between the states get messed up by noise. It's the clock for coherence itself. And once that T2 clock runs out, your superposition is toast, even if the qubit still has energy.
So how on earth do you fight back against the entire universe spying on you? Well, you have to build a fortress. It's an all-out war fought on multiple fronts. First, the brute force approach, cryogenic cooling. They freeze these things down to a fraction of a degree above absolute zero just to make all the atoms stop jiggling around. Then they build a literal fortress with EM shielding to block any stray radio waves or magnetic fields. They go to incredible lengths with materials engineering, using the purest materials on Earth to avoid any internal defects. And even after all that, errors still happen. So, as the last line of defense, they use incredibly clever quantum error correction codes to constantly check for and fix the damage decoherence causes.
All right, so let's just quickly recap the whole journey. Number one, coherence. That's the secret sauce, the quantum magic that makes superposition possible. Number two, decoherence. That's the universe constantly spying on everything, which kills the coherence and forces a quantum system to pick a side and become classical. Third, this whole process is exactly how our solid, predictable reality emerges from that weird quantum foundation. And finally, fighting this decoherence is without a doubt the single biggest challenge we face in building quantum computers that can actually change the world.
So I want to leave you with one final, kind of mind-bending thought. If our classical reality is just what's left over after information has leaked out of the quantum world, what does that mean? Is it possible that the solid world we see and touch every day isn't the real thing at all, but just the publicly available information, the echo of a much deeper, weirder, and richer quantum reality that's happening just beneath the surface?